There are three major types of chemical reactions. The first type are precipitation reactions. These are also called double displacement reactions in the sense that our ions are changing partners. The cation and anion from opposite compounds end up bonded together at the end of the reaction. We've studied precipitation reactions in quite a bit of detail. We know that in this reaction shown here, where magnesium chloride undergoes a reaction with silver nitrate to form silver chloride and magnesium nitrate, we know that it's going to be the magnesium and the nitrate that come together to give us one product in this reaction, and the silver and the chloride that come together to give us our other product in this reaction. The second type of chemical reaction is an acid-base reaction or a neutralization reaction. This type of reaction is going to be a major focus for us in the second semester of this class. But briefly, what happens in this reaction is that an acid, which we know is a compound that is covalently bonded but behaves as an ionic compound in water when it releases that H+ ion, which we call a proton. So we have an acid undergo a reaction with a base, and one of the classic bases is sodium hydroxide. In that reaction, it's a little bit like a double displacement reaction in the sense that the hydrogen from our acid and the hydroxide from our base come together to give us a molecule of water. The other ions that are left form an electrolyte for us. So that's going to mean the sodium combining with the chloride to give us sodium chloride. The third type of chemical reaction are the redox reactions that we've been studying. We know that this is where electrons are transferred from one component in our reaction to another. We know that in order to identify a redox reaction, we must look at our oxidation states and we must calculate changes in our oxidation states from start to finish in the reaction. We know how to identify the oxidation process, where we see an increase in our oxidation state, and we know how to identify the reduction process, where we see a decrease in our oxidation state. We know that oxidation and reduction has a mnemonic that is oil rig. Once we find changes in our oxidation states, we can classify our redox reactions according to four types of reactions. The first is a combination reaction, where two substances combine to form a single substance. This is like a synthetic reaction. So in the reaction shown here, pause the video and determine the oxidation states for all of the components. Identify the oxidation and the reduction process. So when we look at the oxidation states, sodium in an elemental state has an oxidation state of 0, chlorine in an elemental state has an oxidation state of 0, and we know that both of these components on the product side have an oxidation state that is not 0. So that's an easy way for us to know that this is going to be a redox reaction. When we look at the changes that have occurred, sodium started out with an oxidation state of 0, ends up with an oxidation state of +1, which is an increase in its oxidation state and consistent with the oxidation process. Chlorine's oxidation state started out at 0, ended up at -1, and that's a reduction in its oxidation state, and so that's consistent with our reduction process. My sodium has undergone the oxidation. That tells me that my sodium will also be my reducing agent. My chlorine has undergone the reduction and will also be my oxidizing agent. The second type of redox reaction I can have, again, once I've confirmed that this is a redox process, is a decomposition reaction. This is where a single compound reacts to give two or more products. So what we see here is a reaction of mercury 2 oxide in order to give elemental mercury and elemental oxygen. Pause the video and determine the oxidation states for all of the components. Identify the oxidation and the reduction process. In this reaction, we see that the mercury starts out with an oxidation state of +2, ends up with an oxidation state of 0. Its oxidation state has decreased, and we know that that is consistent with a reduction process. My oxygen starts out with an oxidation state of -2, ends up with an oxidation state of 0, and that's consistent with an oxidation process. Again, we see that we have components present in an elemental state on the product side of this reaction, and most simply, we know that these components are present in a compound on the reactant side of the equation. So we know that their oxidation states are not zero here, and we easily know that their oxidation states are zero on the product side of this reaction. Because this is a decomposition reaction and we have a single component falling apart to give two or more products, the mercury 2 oxide in this reaction is both my oxidizing agent and my reducing agent. Number 3 is a single displacement reaction. This is in contrast to the double displacement reaction we saw with our precipitation reactions. In a single displacement reaction, we have an element that reacts with a compound and displaces the element. So in the reaction that we see here, we have copper displace the silver in my silver nitrate compound to give me a molecule of copper 2 nitrate as the product. And then I have silver, which was originally part of my ionic compound, present in an elemental state at the end of this reaction. Pause the video and determine all of the oxidation states for the metals in this reaction. You do not need to determine the oxidation states of the nitrate ion because they will remain unchanged in this reaction because we have nitrate on the reactant side, nitrate on the product side, and anytime we're dealing with a polyatomic ion, the oxidation states of the elements are the same in any nitrate ion in this case because the bonding within a nitrate ion is always the same. So we see that the copper starts out with an oxidation state of 0 on the reactant side, ends up with an oxidation state of +2 on the product side. That's consistent with an oxidation process. Silver starts out with an oxidation state of +1 on the reactant side and ends with an oxidation state of 0 on the product side. That's consistent with a reduction process. So overall in this reaction, my copper has undergone the oxidation. That means that it will be my copper that is my reducing agent. My silver nitrate has undergone the reduction, so that means that my silver nitrate will be my oxidizing agent. Finally, the fourth type of redox reaction is a combustion reaction. This is a reaction with oxygen to form one or more oxygen-containing products, and this reaction usually produces heat and a flame. We've previously talked about the combustion of hydrocarbons in this class. Pause the video and determine the oxidation state for each of the atoms in this reaction. So in this reaction, the carbon starts out with an oxidation state of -4 and ends up with an oxidation state of +4. That represents an increase in its oxidation state, which is consistent with the oxidation process. My hydrogen in this reaction starts out with an oxidation state of +1, ends up with an oxidation state of +1, so that remains unchanged. My oxygen starts out with an oxidation state of 0, and most simply we know that its oxidation state is not 0 on the product side of this reaction, so that's an easy way for us to confirm that this is in fact a redox reaction. My oxygen starts out with an oxidation state of 0, and it ends up with an oxidation state of -2 in carbon dioxide, as well as -2 in the water. That's consistent with a reduction. So overall in this reaction, it would be the methane, the CH4, that has undergone the oxidation, and I would classify as my reducing agent. The oxygen in this reaction has undergone the reduction, and so I would call the oxygen my oxidizing agent. In fact, another way that you can think about an oxidation process is sometimes we see an increase in the number of bonds to oxygen when something has been oxidized. We see here that in this reaction, the carbon has definitely increased its bonds to oxygen. Oxygen has reduced the number of bonds to oxygen with respect to itself, so it has undergone a reduction process. We can't always use that, but we can see that idea clearly in this particular reaction.